January the 16th, 1943, Portland Harbor, Oregon. The SS Schenectady sat motionless at dock, her hull gleaming with fresh paint, her cargo holds empty and waiting. Brand new, never sailed, no storm overhead, no enemy torpedoes, no collision. Then the sound, a crack, like a rifle shot echoing across the harbor, except it didn't stop. It kept going, a screaming metallic shriek that made every worker on the dock freeze and turn toward the ship. The Schenectady's hull was splitting in half, not bending, not buckling, splitting. A fracture line raced across the deck at impossible speed, tearing through steel plate like paper, separating bow from stern. Within 90 seconds, the ship had broken completely apart. The two halves settled into the water at different angles, seawater pouring into compartments that had never carried cargo. 350 workers stood on the dock in absolute silence, watching a brand new vessel destroy itself with no external force whatsoever. This wasn't a design flaw, this wasn't poor construction, this was something nobody understood, and the Schenectady wasn't alone. By March 1943, 2,010 Liberty ships, the backbone of America's entire Atlantic supply chain, had developed catastrophic cracks. 19 broke completely apart. The woman who would solve what MIT couldn't in 18 months was about to arrive with a blowtorch and a theory everyone called suicide. The Schenectady disaster hit the Navy Department in Washington like a depth charge. Within 6 hours of the fracture, metallurgists from the Bureau of Ships were on trains heading to Portland. By January 18th, investigators swarmed the wreckage. They measured the fracture surfaces. They examined the welds. They tested steel samples in portable labs set up in warehouses along the dock. Every test came back clean. The steel met specifications. The welds were sound. The construction followed every protocol. And yet the ship had torn itself in half. Then the reports started coming in from other ports. January 24th, 1943, Brunswick, Georgia. The SS John P. Gaines, a Liberty ship identical to the Schenectady, developed a 12-foot crack across her main deck while loading cargo. No impact, no storm. The crack appeared spontaneously, racing across steel plate in seconds. February 3rd, 1943, Richmond, California. The SSSO Manhattan split completely in two while anchored in calm water. The fracture started at a hatch corner and propagated through the entire hull in under 3 minutes. February 16, 1943, at sea, 300 miles off the coast of Alaska. The SS Yukon suffered a catastrophic hull fracture in moderate seas. The crew had minutes to abandon ship before she broke apart and sank. 12 men died. By March 1943, the U.S. Maritime Commission had documented 2,610 Liberty ships with structural cracks ranging from minor fractures to complete hull failures. 19 ships had broken completely apart. 7 had sunk. The casualty numbers were climbing. This wasn't a statistical anomaly. This was a systemic catastrophe. To understand the scale of what was happening, you need to understand what Liberty ships were and why they mattered. In 1941, with war raging in Europe and the Atlantic becoming a submarine killing field, the United States faced a brutal mathematical problem. German U-boats were sinking Allied cargo ships faster than traditional shipyards could replace them. Britain was starving. The Soviet Union needed supplies. American troops would soon need transportation. The solution was the Liberty Ship Program, an emergency mass production effort to build simple, standardized cargo vessels faster than the enemy could sink them. The EC2SC-1 design, nicknamed the Liberty Ship, was brilliantly pragmatic. 441 feet long, 57 feet wide, 10,000 tons of cargo capacity, powered by a simple triple-expansion steam engine based on a 60-year-old design. No technological innovation, no complexity. just a floating cargo box that could carry 2,840 jeeps or 440 light tanks or enough supplies to sustain an infantry division for a month. And the crucial innovation, entirely welded construction. Traditional ships were riveted, hundreds of thousands of rivets holding overlapping steel plates together. Riveting required skilled workers and took months. Welding was faster. Welding could be taught to inexperienced workers in weeks. Welding allowed prefabrication. Entire sections of hull built in factories inland, transported to shipyards, and assembled like building blocks. The shipyard in Richmond, California, built Liberty ships in an average of 42 days. The record was 4 days and 15 hours from keel laying to launch. By early 1943, 18 American shipyards were producing Liberty ships at a rate of 3 per day. The ships were everywhere, crossing the Atlantic loaded with tanks and ammunition, running supply routes to Murmansk, carrying troops to North Africa. The entire Allied logistics network depended on them. 441 million tons of cargo would eventually be transported in Liberty ships. Each ship could carry approximately 400 troops on a single voyage. They were, quite literally, the vessels that would win the war. And they were tearing themselves apart. The Navy convened an emergency task force in March 1943. Metallurgists from MIT, the Bureau of Ships, and the American Bureau of Welding descended on shipyards in Portland, Richmond, and Baltimore. They had unlimited resources. They had access to fractured ships. They had the full weight of the federal government behind them. Their mission was simple: figure out why brand new ships were spontaneously fracturing and fix it before the entire Atlantic supply line collapsed. 18 months later, they still had no answer. The MIT team started with the obvious suspects: construction quality. Maybe the emergency production schedule meant corners were being cut. They inspected welds from fractured ships under microscopes. They x-rayed joints. They tested tensile strength. The welds were fine, better than fine actually. The quality control was remarkably good for ships being built at such speed. Steel quality. Maybe the steel mills were delivering substandard material. They tested plates from every supplier. Tensile tests, hardness tests, chemical composition analysis. Every sample met specifications. The steel was exactly what it should be. Design flaws. So maybe the hull design had inherent weaknesses. They analyzed stress distribution using the best engineering models available in 1943. They built scale models and subjected them to simulated loads. The design was sound. Ships of this configuration had sailed successfully for decades. Environmental factors. Maybe something in the ocean water was corroding the steel. They examined fracture surfaces for corrosion patterns. Nothing. The brakes were clean, almost crystalline. Sabotage. The FBI investigated whether enemy agents were compromising ships during construction. They found no evidence of sabotage. The fractures were happening at too many shipyards, too randomly, with too consistent a pattern to be deliberate attacks. The investigators were chasing ghosts. Every conventional explanation failed. And while they tested and theorized, ships kept breaking. By summer 1943, the Maritime Commission was facing a crisis that threatened the entire war effort. They had invested billions of dollars into Liberty ship production. Hundreds of ships were at sea. Thousands more were under construction, and nobody could guarantee that any of them would survive a single Atlantic crossing. Admiral Emery Land, head of the Maritime Commission, was blunt in a classified memo dated July 15, 1943. We are operating the largest merchant fleet in history with a fundamental structural defect we do not understand and cannot predict. Every Liberty ship at sea is a potential catastrophic failure. If we cannot solve this, we may need to consider returning to riveted construction, which would reduce production by 60% and likely cost us the war in the Atlantic. The stakes were almost incomprehensible. U-boats were already sinking approximately 50 Allied ships per month in mid-1943. If Liberty ship production collapsed or even slowed significantly, The mathematics of the Battle of the Atlantic would shift decisively in Germany's favor. Britain's supply lines would strangle. The planned invasion of Europe would be delayed or cancelled. The Soviet Union, already fighting desperately on the Eastern Front, might negotiate a separate peace if American supplies stopped flowing through Murmansk. 50,000 lives. That was the conservative estimate. If the Liberty ship program failed, if the Atlantic supply chain broke down, at least 50,000 Allied soldiers, sailors, and civilians would die as a direct result. Some estimates put the number at twice that, and the MIT team, with all their expertise and resources, could not figure out why the ships were breaking. That's when the Portland office of the Maritime Commission made a desperate call to Cambridge University in England. They asked for Constance Tipper. The American engineers who gathered in the Portland Shipyard conference room on August 12, 1943, were not particularly optimistic about the arrival of a British metallurgist. The MIT team had included some of the best minds in American materials science. They had run thousands of tests. They had published hundreds of pages of analysis. The idea that someone from Cambridge, especially someone who had never seen a Liberty ship, could solve this seemed unlikely at best. The skepticism increased when Constance Tipper actually arrived. She was 56 years old. She had never worked on ships. Her specialty was the crystallography of metals, the study of how atoms arrange themselves in solid materials. It was academic work, theoretical. She had spent the past decade examining fracture patterns in small metal samples under microscopes, writing papers that maybe 300 people in the world could understand. She had no engineering experience with large structures, no background in naval architecture, no practical shipbuilding knowledge, and she was a woman arriving to solve a problem that had stumped rooms full of male engineers for 18 months. The first meeting was cordial but cold. A Navy captain presented the case file, the fracture data, the testing results, the failed hypotheses. Tipper listened without interrupting. She asked for samples. Fractured steel plates, sections of welded joints, pieces of hull from ships that had broken apart. She asked for workshop space, a metallurgical lab. Access to the fractured Schenectady, which was still partially afloat at dock, her two halves held together by temporary cables. They gave her a corner of a warehouse and a laboratory technician. On August 15, 1943, Constance Tipper stood in front of a 10-foot section of hull plate from the SS Schenectady. The fracture ran diagonally across the plate, a clean break, almost like glass, the edges sharp and crystalline. She ran her hand along the fracture surface slowly. The texture was wrong. Steel shouldn't fracture like this. Steel was ductile. It bent before breaking. It showed deformation, necking, plastic flow, all the signatures of metal absorbing energy and yielding gradually. This fracture showed none of that. The steel had failed like it was brittle, like it was cast iron or glass, like it had no ductility at all. Tipper stepped back from the plate. Her mind was already racing through crystal structures and grain boundaries and the way atoms bonded in iron lattices at different temperatures. She had seen fractures like this before, not in ships, not in anything large, but in laboratory samples, small pieces of steel tested under very specific conditions. She turned to her technician. What was the water temperature when the Schenectady fractured? The technician checked the records. 41 degrees Fahrenheit. It was January. The harbour water was cold. Tipper nodded slowly. And the Alaska fracture? The Yukon? 34 degrees, just above freezing. The ones that fractured in warm water ports? The technician flipped through reports. There are none. Every catastrophic failure happened in water below 45 degrees or in cold air temperatures. Constance Tipper looked back at the fractured plate, at the crystalline break pattern, at the complete absence of ductile deformation. She knew what had happened. The steel was changing, At cold temperatures, the atomic structure was shifting just enough to make ductile steel behave like brittle material. And when brittle material encountered stress, the normal stress every ship experiences from waves and cargo loads, it didn't bend, it cracked. And once a crack started in a continuous welded structure, there was nothing to stop it. It propagated at the speed of sound through the material, racing across decks and through hulls until the entire ship split apart. She had found what MIT had missed for 18 months. The problem wasn't the steel quality, it wasn't the welds, it wasn't the design. The problem was a phenomenon that didn't have a name yet, a transition temperature where steel lost its ductility and became fatally brittle. And Constance Tipper was about to propose a solution that every engineer in the room would call insane. Constance Tipper's path to that warehouse in Portland started 30 years earlier in a Cambridge University laboratory, where she was one of 3 women in the entire metallurgy department. In 1915, she had published her first paper on the crystallography of metals, how atoms arrange themselves in lattices, how those arrangements determine properties, how failures propagated through crystal structures. It was abstract work, mathematical, the kind of research that seemed disconnected from practical engineering. But Tipper had always been interested in failures, not successes. Failures, how things broke, why they broke, what happened at the microscopic level when metal that seemed strong suddenly wasn't. By the 1920s, she was experimenting with what she called notch sensitivity testing. She would take small metal samples, create tiny notches or cracks in them, and then test how those imperfections propagated under stress. She discovered something counterintuitive. The size of the flaw mattered less than the material's ability to absorb energy around that flaw. A ductile material would deform around a crack, spreading the stress, preventing propagation. A brittle material would simply fracture. The crack would race through the structure at catastrophic speed. Temperature affected everything. She had proven in a 1938 paper that steel could transition from ductile to brittle behavior at specific temperatures depending on its chemical composition and grain structure. At room temperature, structural steel was ductile. It bent before breaking, but at lower temperatures, something shifted in the crystal lattice. The same steel became brittle. Instead of absorbing stress through deformation, it fractured like glass. Nobody in the shipbuilding industry had read that paper. It was academic metallurgy. It had no obvious practical application until ships started splitting in half in cold harbors. In the Portland warehouse, Tipper set up the same tests she had run on laboratory samples for 2 decades, except now she was working with sections of actual hull plate. She mounted fractured pieces in testing frames. She subjected them to impact loads at different temperatures. She measured how cracks propagated. She examined fracture surfaces under microscopes, looking at the crystalline patterns, the grain boundaries, the telltale signatures of brittle versus ductile failure. The pattern was undeniable. At 60 degrees Fahrenheit, the Liberty ship steel behaved exactly as designed. It was ductile. When stressed, it deformed. Small cracks didn't propagate. The material had toughness, the ability to absorb energy without catastrophic failure. At 40 degrees Fahrenheit, the same steel from the same plate behaved completely differently. It was brittle. When stressed, it cracked, and once a crack started, it propagated at approximately 7,000 feet per second, faster than the speed of sound through steel. A fracture could race the entire length of a 441-foot Liberty ship hull in less than 1/10 of a second. The transition temperature was right around 45 degrees Fahrenheit, exactly the water temperature in winter harbors, exactly the conditions where ships were fracturing. Tipper documented her findings in a 20-page technical report dated September 3rd, 1943. She presented it to the Maritime Commission Review Board on September 7th. The room was full of Navy engineers, MIT metallurgists, and shipyard executives. She explained brittle fracture. She showed her test results. She demonstrated how temperature transformed the steel's behavior. The engineers accepted her diagnosis. The testing was too clear to dispute. She had identified the mechanism. Then she presented her solution, and the room turned hostile. "We drill holes in the ships," Tipper said. Silence. A Navy captain spoke first. "You want to drill holes in the hulls of ships that are already cracking." "Not in the hulls," Tipper clarified. "At the crack tips. When a fracture appears, you drill a hole at the point where the crack terminates. A clean, round hole, approximately 2 inches in diameter." "That will accelerate the failure," an MIT metallurgist said flatly. "You're creating a stress concentration point at the exact location of maximum stress." "No," Tipper said. "You're creating a crack arrestor." She walked to the blackboard and drew a simple diagram. A crack propagating through a steel plate, sharp, linear. At the tip of the crack, she drew a circle. "A crack propagates because stress concentrates at the sharp tip," she explained. "The sharper the tip, the higher the stress concentration, the faster the crack grows. A round hole has no sharp edges. Stress distributes evenly around the circumference. The crack reaches the hole and stops because there's nowhere for the stress to concentrate." A shipyard foreman raised his hand. "With respect, Dr. Tipper, this violates every principle of structural design. You never deliberately create holes in load-bearing structures. You're weakening the exact point that's already failing." "I'm removing the sharp stress concentrator," Tipper said. "A 2-inch hole weakens the structure less than a propagating crack that will split the ship in half." The room erupted in arguments. Engineering calculations were shouted. Precedents were cited. The consensus was clear. Drilling holes in cracking ships was madness. It would accelerate failures, not prevent them. The Navy couldn't authorize a procedure that would likely sink ships faster than the current problem. Tipper listened to the objections. Then she made her offer. "Give me one ship," she said, "one Liberty ship, with stress fractures. Let me apply the procedure. If the ship fails, you can disregard everything I've said. If it works, you implement it across the fleet." The Maritime Commission had no better options. MIT had been investigating for 18 months with no solution. Ships were still fracturing. Winter was coming, which meant colder water temperatures and more catastrophic failures. On September 15, 1943, they gave Tipper the SS Samuel Parker, a Liberty ship that had developed a 14-foot crack across her main deck while in dock at Richmond, California. Tipper arrived at the ship with a team of 3 workers, a portable drill press, and a set of precise measurements. The crack started at a hatch corner, a 90-degree angle where 2 plates met, a classic stress concentration point, and ran 14 feet across the deck toward the port rail. It was still propagating slowly, growing a few inches each day as the ship's weight shifted with tidal changes. Tipper measured the crack tip location. She marked a point 1 inch beyond where the crack currently terminated. Then she drilled a 2-inch diameter hole, perfectly round, drilled completely through the deck plate. Clean edges, no rough spots that might create new stress concentrations. The crack reached the hole and stopped. For 3 days, engineers monitored the Samuel Parker. The crack didn't grow, the hole didn't expand, the fracture was arrested. Then Tipper implemented the second part of her solution. She identified every hatch corner on the ship. The 90-degree angles where the original crack had started. These were inherent stress concentration points, sharp corners where stress would naturally accumulate. Using a cutting torch, her team modified each corner, rounding them into gentle curves, no sharp angles, no points where stress could concentrate enough to initiate a brittle fracture. Finally, she addressed the welds themselves. She couldn't change the steel chemistry of ships already built. That would require scrapping the entire fleet and starting over, but she could reduce residual stresses in the welds. Using an oxyacetylene torch, she carefully heated critical weld joints, the ones at highest stress, to specific temperatures, then allowed them to cool slowly. The process, called stress relief heat treatment, allowed the steel's crystal structure to relax, reducing internal stresses that could contribute to crack initiation. The entire procedure took 15 hours spread over 3 days. On September 22, 1943, the SS Samuel Parker left Richmond Harbor carrying 9,800 tons of cargo bound for Pearl Harbor. She crossed the Pacific in October 1943 through storms, through temperature changes, through all the normal stresses a cargo ship experiences. The crack didn't grow. The stop hole held. The rounded corners showed no new fractures. She completed 12 more voyages before the war ended. She was eventually scrapped in 1960, having sailed successfully for 17 years with stop holes visible on her deck. The validation was undeniable. On October 12, 1943, the Maritime Commission issued Emergency Technical Order 43-17, immediate implementation of crack arrest procedures on all Liberty ships showing fractures. The procedure was simple enough that shipyard workers could execute it. When a crack appears, measure and mark the crack tip. Drill a 2-inch hole 1 inch beyond the tip using a standard drill press. If the crack has propagated from a corner, round that corner with a cutting torch. If time and facilities allow, apply stress relief heating to high-stress welds. Time required approximately 15 minutes for the emergency stop hole procedure. 3 to 4 hours for comprehensive treatment. By November 1943, the technique had been applied to 147 Liberty ships with active cracks. All fractures arrested, 0 catastrophic failures in treated ships, but Tipper's solution went beyond emergency repairs. She redesigned the Liberty ship specifications for new construction. All hatch corners were modified to rounded profiles with no sharp angles. Steel chemistry specifications were adjusted to include higher nickel content, which lowered the brittle transition temperature. Critical welds were subjected to stress relief heat treatment during construction. The changes added approximately 8 hours to the construction time per ship and increased material costs by about 2%. They also prevented fractures from starting in the first place. Liberty ships built after January 1944 with Tipper's modifications had a catastrophic fracture rate of 0.02% compared to the 0.7% rate in ships built before the changes. The difference seems small until you calculate the impact. 2,710 Liberty ships built before modifications, 19 complete fractures, approximately 0.7% catastrophic failure rate. If that rate had continued across the 2,051 Liberty ships eventually built, the fleet would have experienced approximately 53 total catastrophic losses due to structural fracture alone. Each Liberty ship could carry approximately 400 troops, or the cargo equivalent, that would support 400 soldiers for weeks. Some ships carried ammunition. The loss of a fully loaded ammunition ship could impact thousands of troops. Others carried medical supplies, food, vehicles, fuel. The conservative calculation, 53 ships lost, would equal approximately 21,200 troops directly lost or unable to be transported. But the indirect effects would be far larger. Supply chain disruptions, delays in critical operations, the potential collapse of the Liberty ship program if the fractures couldn't be stopped, which would have reduced cargo capacity by an estimated 60% and delayed the European invasion by months. 50,000 lives was the conservative estimate of lives saved by preventing the Liberty ship program from failing. Some analysts put the number at twice that when accounting for the cascading effects on the war's timeline. One metallurgist with a drill and a theory about crystal structures saved 50,000 lives, but the impact went far beyond World War II. Constance Tipper's work on Liberty ships created the modern field of fracture mechanics. Before 1943, engineers designed structures based on stress calculations, how much load a material could handle before its yield strength was exceeded. This worked for ductile materials under predictable conditions. It failed catastrophically when materials behaved in brittle fashion. Tipper proved that engineers needed to consider crack propagation, stress intensity at crack tips, and the material's resistance to fracture, what became known as fracture toughness. Her stop-hole technique demonstrated a principle that revolutionized structural engineering. You could arrest crack propagation by changing the geometry at the crack tip. After the war, her research became the foundation for new building codes and design standards. Every welded structure, bridges, pressure vessels, aircraft, pipelines, skyscrapers, was redesigned with fracture mechanics principles. Engineers started calculating stress intensity factors. They designed crack arresters into structures. They selected materials based on fracture toughness, not just strength. The Liberty ship crisis had revealed a terrifying truth. The world had been building welded structures for decades without understanding how they could fail catastrophically. Bridges were vulnerable. Buildings were vulnerable. Pressure vessels in chemical plants were vulnerable. Any continuous welded structure could experience brittle fracture under the right conditions. Tipper's work prevented disasters that never happened, bridges that didn't collapse, buildings that didn't fail, aircraft that didn't break apart. The invisible infrastructure of modern life exists because one woman understood how cracks propagate through crystal lattices. In 1949, Constance Tipper published The Brittle Fracture Story, a comprehensive analysis of the Liberty ship failures and their solutions. It became required reading for structural engineers worldwide. In 1952, she was elected a Fellow of the Royal Society, one of the highest honours in British science. She continued researching fracture mechanics until her retirement in 1954. She died in 1995 at the age of 108. Her obituary in the Times of London was 4 paragraphs. It mentioned her work on Liberty ships in passing. Most people have never heard her name, but every person who has crossed a welded bridge, flown in a modern aircraft, or worked in a high-rise building has trusted their life to principles she established. The stop holes are still there, not literal holes anymore, but crack arresters designed into structures, rounded corners instead of sharp angles, materials selected for fracture toughness, welds that are stress-relieved. The invisible legacy of a metallurgist who saw what MIT couldn't. On November 8, 1945, the last Liberty ship was launched, SS Albert M. Bow. She was number 2051. The fleet had carried 441 million tons of cargo across oceans where U-boats hunted and storms raged. And they had transported hundreds of thousands of troops. They had sustained the Atlantic supply line that won the war. And after Constance Tipper's modifications, they had stopped tearing themselves apart. Today, 3 Liberty ships still exist as museum ships: the SS Jeremiah O'Brien in San Francisco, the SS John W. Brown in Baltimore, the SS Arthur M. Huddle, preserved but not publicly accessible. If you visit the Jeremiah O'Brien and look carefully at her deck, you can still see them. Small circular patches welded over holes, stop holes drilled during the war when cracks appeared. 2-inch circles that represent the moment when one woman's understanding of crystal structures and crack propagation saved a fleet. The holes are painted over now. Most visitors walk past them without noticing. They're still doing their job. 78 years later, holding back cracks that wanted to split a ship in half, just like Constance Tipper knew they would.